Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we're going to be continuing doing some AMC 10 and 12 problems, gearing up for the exam this fall. So, quick little reminder, the exams are coming up in November, 10A, 12A on the 10th, 10B, 12B on the 16th, and check out our blog, and there's specifically a blog post with some tips and tricks for preparing for the exams this fall. Now, let's jump right in to our first problem. This comes from the AMC 10B. It is a probability question there, and is one that it's good and important to read carefully. Make sure you get things correct that way as well. So Deborah flips a fair coin. She's counting the number of heads and tails she gets. And let's kind of highlight these important pieces of information. So fair coin is fine, but she's either getting 2 heads in a row or 2 tails in a row. At which point she stops flipping. So this kind of is right off the bat getting us to think about alternating, right? If you start with the heads, then if you get another heads, you're done. If you start with the tails and then get another tails, you're done. So anytime you get heads, unless you're finishing, you're getting a tails. So we have this alternating scenario until we stop. Now, there is one additional piece of information that we have to keep in mind here. So we want to know what is the probability she gets 2 heads in a row. So that's what we're looking for. But she sees a second tail before she sees a second head. And that kind of is our starting point of information there. Now, if you think about this a little bit, remember I said we're alternating until we end. So if we see a second tail before a second heads, remember this is before the end, we're getting 2 heads in a row at the end, that means it's going to have to start, and we have a pretty nice beginning that we know her first flip was a tail, the second flip was a head, and the third flip was a tail. So we know that for sure. We know these first 3 flips, right? And we can turn this into a probability right away as well. This has a probability of 1/8. So I like thinking about that as our starting point from there. Now, there's a lot of different things that can happen from here. And for a lot of counting questions, really doesn't hurt to start writing down the things that can happen. Try to see if you can look for a pattern, see if you can look for some similarities and stuff, and that will oftentimes be the way you come up with the solution. You don't see the solution right away, but you just start playing around a little bit. Well, okay, well, if we're getting 2 heads in a row, now we've gotten the second tail before the second heads. Maybe we just get 2 heads in a row there. And right, we could keep track of the probability of that as well. Additional probability. So this would have an additional probability of 1/4. Well, maybe we alternate some more. We got 2 heads at the end, so we can't get a tail. So maybe we have another alternating heads, tails, and then we get 2 heads. And note if we look at this probability, this is 4, 2 to the 4th, 1/16 here. And probably we just need one more example here. We have a couple alternatings, heads, tails, right? Heads, heads in that case. And now we have 2 additional. We have an additional 1/4, and so this is 1/64 here. Now, there are, of course, other ways to do this, but at this point, we can see that that pattern is going to be continuing from there. So if we try to start calculating our probability then here, don't forget our 1/8, so let me just keep that out in front. And then we have 1/4 plus 1/16. And pretty quickly we're seeing here this is a geometric series. We have times 1/4 each time. So let me summarize that on the side here, right? Just to keep in mind that is our geometric series that we're dealing with in this scenario. So when we're adding this up then, right, let's add this up as, and depending on how you like thinking about your geometric series, I like pulling out the 1/4 in a sense, and then our infinite geometric series is 1 over 1 minus the common ratio, so 1/4. So we have 1/32, right? And then this is times 3/4 there. So the 3/4 becomes 4/3, and so we get 1 over 32 times 4/3. 4's cancel, 8 times 3 is 24. So we have 1/24 as our final answer here on the bottom. And always good to just double check that that matches one of our answers. It does. Make sure we're answering the correct question and have it filled in correctly if you're taking the actual exam, and then we're good. So our final answer is B, 1 over 24. Okay, so let's take a look at our next question then too. So this one is a AMC 12A question dealing with some of the kth power of the roots of some of these things there. So we have roots of this polynomial, and I'll come back to that. That is our kind of key thing that we want to think about there. So kth powers of the roots. So let's just kind of start out and kind of think about what we're asked about. So S sub k, some of the kth powers of the roots. And the problem tells us, so the problem's telling us some information that we can actually write this sum of the k plus first powers of roots as this recursive formula in terms of the smaller powers in that case. So let's just kind of write this out, right? So if we name the roots, so let's call them P, Q, and R, and then S will be the sum, right? So we have P, Q, and R are the roots. And then we're looking for sk plus 1, which is the sum of all of the k plus first powers that we have. Now, there's a couple of different ways to do this. One way you could do it is, oh, well, we know that this is true for all of the k values. So you could say, let's try to look at the sum of the cubes and do some direct factoring formulas there and things like that as well. But we actually have a pretty nice trick that we can do and we can look at in general. So let's focus on this k plus first power of p. Of course, whatever we do for one root is going to be the same as the other ones there. But this is a good chance to review what it actually means to be a root of the polynomial, right? So let's write this down here. And what does it mean that p is a root? And I'm going to write this all out because I think it's good to emphasize and kind of keep that clear as well. So what does it mean to say that p is a root of x cubed minus 5x squared plus 8x minus 13? Well, by definition, right, this is a little bit silly, but by definition, this means that if you plug it in, it means that if you plug it in, so we have p cubed minus 5p squared plus 8p minus 13, you get 0. And here's the punchline. Here's the important thing. Notice that this tells us that p cubed is equal to, we can say the third power of p is equal to 5p squared, moving everything to the other side, minus 8p plus 13 in this scenario. But now, wait a second. What if I multiply everything, right? So we are looking at p to the k plus first power. So what if I multiply everything here by p to the k minus 2, right? And again, if you want to look at the specific example, maybe that's an easier way to look at things there. But just to follow the problem, right? If we multiply by p to the k minus 2 on both sides, we actually have p to the k plus 1. So that is our matching p to the k plus 1. And these coefficients are the same. So we have 5 to the p, and then we have k minus 8p to the k minus 1. And then plus 13 to the p times k minus 2, p to the k minus 2 there. But now, right, let's just pause and think about this, because we're actually pretty much done, right? So this is our p to the k minus 1, right? And that could be plugged in here. And similarly, we would have a similar thing that we could do for, right, q to the k minus 1. We would have the exact same thing, right? So I'm not going to write it all out, but q to the, k plus 1 equals 5p to the, or sorry, not p, 5q to the k dot dot dot. And we would have something similar for r to the k plus 1, right? So these are exactly the same things. And those could be plugged in there as well. So we would have the same thing for q to the k plus 1. We would have the same thing for r to the k plus 1. And so we're writing each of those powers in the exact same way as lower powers. And notice that what this gives us is, okay, this is telling us that s to the k plus 1 is what? Well, we have 5p to the k, 5q to the k, 5r to the k. Well, that's just 5s sub k. Then what if we do the same thing for the k minus 1 power? We're going to get minus 8s sub k minus 1. And then we're going to have plus 13 s sub k minus 2. So we're actually then done, right? Our final answer there, 13 minus 8 plus 5. However, whichever order you want to do this in is, of course, good. And so our final answer here is just going to be D, right? 5 minus 8 plus 13, answer choice D there. So this trick of, oh, if you have a root of a polynomial, that gives you an equation to manipulate, right? P cubed is this, you could solve for the constant, right? You can substitute in however you want. And here that allows us to reduce the powers and get our sum as needed. Okay, that will do it for this video. Stay tuned for new problems next week. As mentioned, check out our blog for ways to get access to some mock tests, good practice resources, things like that as well. And I hope to see everybody next week, and let me know if you have any comments or requests in the boxes below. Goodbye, everyone.